we're presenting AI in space, how machines sense, decide, and act beyond Earth.
Before we get into the really cool examples of AI in space, I want to quickly explain what we're actually trying to understand today. By the end of this presentation, we want everyone to understand why organizations like NASA even need AI in the first place. Because when most people hear AI, we think of chatbots, um, i.e., ChatGPT and like Cloud and shit, recommendation systems, image generation. But in space, AI becomes something way more important because it's an actual decision making system. So we'll explore the real ways it's used in space, like helping rovers navigate, planning safe movements, analyzing huge amounts of data and stuff like that. We'll also simplify a few technical ideas, like we'll talk about computer vision, how machines interpret images, and yeah, we'll also talk a bit about risks. That's it. That's the stuff we're covering in this lecture. We can move on.
Yep.
Okay, so this is our opening activity, and we invite you all to think like NASA and what you would do in this situation. So our prompt of discussion is: imagine you are controlling a rover on Mars, and you send a command from Earth, but it takes over 20 minutes to arrive. While the rover is waiting, it encounters a steep slope and loose rocks. So, our question, which we want you to discuss, is: should the rover stop and wait for instructions, or should it decide what to do on its own? So, should the rover take the path that maybe less time consuming but more dangerous, or should it take the path that is longer but safer, and why?
Please answer the question in the chat, or you can unmute yourself.
Can I say anything? Okay.
Yeah, sure, you can answer too.
Um, I was gonna say that the rover should wait perhaps for like instructions, just because the rocks and like the steep slope, it could potentially like damage the rover. So I would say wait, and it's better to be safe than actually like damage it, because if it's damaged and you can't really do anything with it, and your mission would kind of be ruined. So I would say like just to wait for instructions.
I agree because I think you spend so much money building the rover and getting it to Mars, and then for it to just break apart because of some rock would be really devastating. But also at the same time, in like another situation where a rover might not have the time for the message to get back to it, like if it's like in some risk of a situation, then you it kind of needs to come up with something on its own, or else it can be harmful for the rover in the long term.
Hmm.
I want to add this here because you are right, because messages take like 8 minutes, I think, to transfer from Earth to Mars. Like
Hmm.
a one-way journey is 8 minutes and then it goes back. So it's like it takes quite a while. So rovers need to be able to make decisions by themselves as well, because
Hmm.
they don't always have that much time.
Yeah, that the autonomous thinking does kind of help um, a limit or basically minimize like that timing factor in between. Okay. Next slide. Manvita. Sure.
Okay. So for the debrief from the opening prompt, we would like to wait for human instructions, just so the mission is not placed at risk. And this shows that in space, autonomy is not about convenience but survival, because if your rover is damaged, then there's basically no point about it. So that's why it's better to wait. And for why decision making must shift, so communication delays prevent real time human control. And space environments are uncertain and change rapidly, so you should try to be prepared for like any situation that could happen. And systems operate with limited.
Sorry. You see it now?
And these systems operate with limited power, data, and resources. So decisions must be made within strict constraints. You can't you don't you have limited resource and everything, so you can't just choose from whatever you want, but you have to choose from what you have. And for the guiding question moving forward, so the key question is no longer whether AI should make decisions in space, but the real challenge is how these decisions are structured, validated, and controlled. And for the guiding question moving forward, so autonomous navigation and mobility explores how space systems should sense their environment, determine where they are, and choose safe actions without human intervention. And this can save like a lot of time and resources. Just like you said before, it takes like 8 minutes for the signal to reach. So I think that could save a lot of time. And for how space AI makes decisions, um, there should be autonomy under constraints, and you should plan and schedule in advance with limited resources. There should be computer vision for environmental awareness and machine learning to improve decisions over time, anomaly detection to recognize failures early, validation to ensure system reliability, and explainable AI for human trust and accountability.
Okay. So next one is what is autonomous navigation and mobility? So the core concept here is that autonomous navigation and mobility is the ability of a spacecraft
Evan,
or
hang
rover
on,
to.
wait. I'm doing this slide
Okay.
because said I'm doing slide. Yeah, okay. So, autonomous navigation mobility it sounds technical, but it's really straightforward. It's just like the ability of the spacecraft, rover, drone, whatever, to move and make decisions independently. And Vita was kind of talking about that before. It can't wait for humans all the time. So now we want you to sort of answer this question. So, which of these steps do you think matters the most when the rover is alone on Mars? Is it A, environmental awareness, B, self-localization, C, safe path selection, or D, independent action? Uh, Answer in the chat or unmute yourself, your choice.
So someone asked to explain this more in depth. So the first answer choice, environmental awareness, basically means understand what's around it. So if there's like rocks, cliffs, sand, or obstacles. Self-localization, that basically means it knows where it is on the planet, like using a map or like using a GPS system. Safe path selection basically means it chooses like the safest route to travel without getting stuck or damaged. And then the independent action, that basically is it's able to be independent, make its own decision, and carry them out on its own. If that helps with your decision making and in the choices for your answers. Um, so yeah, you guys can answer in the chat. Okay. Petit, I can't really see like the chat. I'm
Yeah,
I'm
they're all saying
presenting.
C or D. Just like you can move. Enough people have responded.
Okay, yeah. C is definitely it's indicating the more safer route. It's obviously gonna have to use some decision to basically find like the most safest ways to navigate around like certain things. So that's probably the more broad option. So that probably fits the best. What do you think? Everyone agree?
I'd say D would also have been like a decent option to choose. Like I can understand why everyone's picked that. I haven't moved to the next slide.
Yeah, I threw you guys off there. Prateep, you want to go ahead and do this one? This was yours, right? Or this is
No,
mine.
it's
This is
yours.
mine. My
It's
bad.
yours.
So the strongest answer is A, environmental awareness, because a rover cannot localize itself, plan a path, or even act independently if it cannot first understand its surroundings. But conceptually and for learning purposes, the correct takeaway is all of the above work together as like really one system. So like in space, these functions must operate together and cohesively in real time. The next step is understanding how the rover will actually interpret its surroundings. So we'll go more into that in the next couple of slides.
Now that we understand the overall process of autonomous navigation, let's zoom in on the very first step. So, uh, how does a rover actually like interpret the environment around it? Because obviously a rover doesn't see Mars the way we do. They usually just collect raw data with cameras and sensors and stuff. They don't really like recognize hills and rocks and dangerous areas instantly. So the next step is understanding how AI actually converts that raw information into like something useful. So let's look at computer vision. I mean, next slide.
So how does AI know where it is basically? So because Mars doesn't have a GPS, right? The AI uses like a process called mapping and localization, where the rover has to create its own map using a different software that obviously computer scientists or engineers may have to implement into these rovers. There's the image on the right that shows how a rover has to determine its position without GPS, um, which it's not using GPS. It's essentially making its own map.
So how AI decides where to go once the rover actually like understands the terrain around it. Uh, I mean, on Earth we rely on GPS. Mars doesn't have a GPS, so rovers have to figure out their position independently. So as Evan was talking about, they use like mapping and localization. Uh, Okay, for example, imagine this. You're like walking around an unfamiliar place, okay? You might think like, okay, I passed it. Like, say you're walking around in like the neighborhood over here, and you think, okay, I passed the tree already, or that building looks familiar. You might think stuff like that. Rovers actually do something very similar, but it's like mathematically. So they compare new camera images with older ones and look for familiar landmarks like rocks and stuff. So now once it understands all the terrain and location, it actually chooses a path. So they actually evaluate multiple routes and compare them based on safety risk, distance to the target, and the actual energy that's connected to distance, kind of. But yeah, the energy it would require to travel, and it chooses the best route that minimizes all of that. Now, this image represents how NASA's rover actually determined its position during operations in the Jezero crater. And as it moved, the algorithms compared camera images of the terrain around it to previous views in order to track its movement. This allowed it to sort of estimate where it was relative to features even without GPS. Next slide.
Yeah. So here's like another method that is used. It's called a SLAM, and it actually stands for a simultaneous location and mapping. It's a method that a rovers use to build a map of its surroundings, and it updates in real time. So think of like Google Maps, where you're able to see a live traffic feed, or you're able to see how busy somewhere is, kind of like that. But obviously, there has to be more things taken into account because we're in space first of all. So like the different variabilities in that. but also they have to go through various processes and also update its map to using sensors and camera images, not just to compare, right? Google Maps, they use like alerting systems, so where someone can alert Google about like a potential accident 5 minutes away. For this, is more of relying on camera images and sensors to basically decide where it needs to go. So that's like the more complex part about it.
So far, we've only been talking about like rovers moving across surfaces, but it's also important for how the spacecraft actually like lands on the planet in the first place. So that's really different because everything happens really fast when it's landing because I mean it's falling. So like I mean, it enters the atmosphere at a very high speed, uh, and the thrusters have to guide the landing, often within just a few seconds. So humans simply just can't react quickly enough to control this manually from Earth. As I said before, like the 8 minutes thing, it's just not feasible for us to control all of that. So AI helps make the decisions for thruster control simultaneously, and uh, the basic processes are first the cameras capture the images of the surface below, then the AI compares them to images on stored maps and analyzes the terrain, and it calculates the safest landing spot and adjusts the movement using the thrusters. And all of this happens within seconds. In space exploration, as I've sort of said before, milliseconds matter. So, like a small mistake during landing can mean complete mission failure. So, yeah, yeah, you can move on.
This is your next slide, Patika, to do simulation. Okay.
Oh yeah, uh, yeah. Play the yeah. So one of the best examples of autonomous navigation is NASA's Perseverance rover. We've been talking quite a bit about that. It landed near the Jezero crater, as we said, and that's because scientists once believed that that place contained water. The challenge was that this area is scientifically valuable but also dangerous because there are steep slopes, rocky terrain, and places where a bad landing could completely destroy the mission. So NASA actually used AI systems to help guide the landing. So like during descent, for instance, the cameras captured images of the Martian surface, and AI then compared those images to maps beforehand and calculated the safest landing spot. Even after landing, Perseverance obviously continued using autonomous navigation. Yeah, you can move
Next
on.
slide. So this is like some simulations that we want you guys to like kind of play around with. I'm going to paste both of the links, but I'm actually going to show you guys first about it. So you guys may not be able to see my screen. Let me go back here and just do the window itself. So this was the first link. This is basically you're able to see the current and path locations of Perseverance on this interactive map. So this is where Perseverance is right now as we speak. Right now, gives you latitude and longitude. It gives you its previous pass. You can see. You're able to scroll out and stuff, like see where it like took different samples. Where like it landed at right here. So it's like pretty cool. You're able to see this in terms of, like mapping. Um, so yeah, you can like zoom like all the way out, and it may load, it may not load. You're able to see where its path was. Yeah, so I'll put that link in the chat in 1 second. Let me show you the last one. The last one is just like a informational thing. It's on Google. Let me go back out here. Okay. Oh no, it's not here anymore. Actually, yeah, here it is. So this is like a 3D model. You're able to view it, just like basically how it's composed for Perseverance. Um, so yeah, I'm not sure. You were able to see it on here. I don't know where it went, but it was like this. It was like one of those a special Google links you're able to click on, and you're able to see about it. Let me try to look it up exactly. That is actually sad. So I don't think it's there anymore, but this is like what it looked like. You're able to basically move it around and click on like different things, like learn about it. Um, so yeah, I'm gonna put the two links in the chat. You guys can like play around with that for a little bit. put it in the chat real quick. That's the one for the Google one, and then here's the one for um, the current mapping locations. Um, yeah, and then one bonus uh, is it's on mobile devices only. It might still be available. They had to do with a recent patch update, but it's on the USA Today app. You're able to basically look through the uh, the Mission to Mars AR app. We're able to actually see the Perseverance on its current location in Mars. So yeah, it's called Mission to Mars AR app.
We'll show all of these apps again at the end of the slideshow because really want y'all to explore that. But for now, we'll move
Yeah.
on. Uh,
Yep. All right, let's get back to
yeah.
showing.
Yeah, Evan, I think you're doing this one.
Okay, yeah. Okay. The AI in planetary robotics and surface tasks. So, what tasks does AI enable on the surface? So, AI allows for a robot to perform physical work after landing, right? So, this includes drilling into rocks, moving materials, basic construction setup, right? But here's where the autonomy comes in, which is like without the human control. It can be critical due to long communication delays. As we said before, it takes about 20 minutes to actually get like a human controlled message to the Mars rover. It can be harsh and unpredictable terrain. This is where like the sensors come in. Also limited human oversight with autonomy. So it's not going to rely on like 20 minutes sending messages to the actual rover. It's going to basically allow the rover to basically do a thing for itself. So that like the key point here is that AI turns robots into active workers, not just explorers. So yeah.
So AI actually like helps robots perform physical work. So, for example, robots may drill into rocks, collect samples, move materials, all that. Uh, s- and then also there are communication delays. The thing is that these robot arms, they actually have like multiple functions. You know, they like drill into rock. They also like grab stuff and they store them inside the robot securely. And the problem is that these have to operate in extremely like cold conditions and hot conditions. Because I don't think the Martian atmosphere is as thick as the one in Earth. So there's problems with radiation and everything. It's also dusty, and the marsh. There are different gravity conditions over there. Now, sample collection is like a direct application of robotic arm control, because like the arm itself does it. It's not like a separate system in the robot. So they have to. Basically, the point of the slide is to show that the robot arm has to be well engineered. It has to have multiple functions and withstand harsh conditions. Yeah.
Yeah. So, what surface robots have sampled and returned to Earth? So here is like an example of what I particularly talked about on the last slide. So the first sample that was collected was moon rocks and soil from the Apollo mission, and also one from the Soviet Luna robotic landers. So that's what it kind of looks like there. Also comet dust that was also taken from surface robot from the Stardust mission. So that's what it kind of looks like there. Um, it was I forgot how big or small it was, but yeah, olivine is definitely like a rare metal. I know that for a fact. I'm in geology right now. Anyways, um, asteroid material. So this was taken during the Osiris Rex mission and the Hayabusa and Hayabusa 2 um, missions, and those were both samples taken and brought back to Earth. So yep, the next slide. This is talking more about the, uh, the Osiris Rex on the Hayabusa missions and the case studies.
So the Osiris Rex, it touched down on the asteroid Bennu, and it used an autonomous arm to collect surface regolith. I guess that's just rocks. So The AI actually controlled the contact timing and forced to prevent the spacecraft from drifting away. Now, Hayabusa 2, this wasn't NASA, this was JAXA. I forgot which country that was from. Anyhow, it landed on asteroid Ryugu and collected surface samples, and it was different. It deployed like small hopping robots to explore the surface, and those used autonomous navigation because of extremely low gravity. So these are some of the samples that from the Ryugu astronaut, and yeah, you can move on.
Okay. The next slide is going to be a activity with Mokon. So you guys will like this activity a lot. It'll work.
Okay, guys, my name's Mokund. Yeah, so this activity is just maybe talking with some people, getting to know each other, and then trying to figure out what's the best route for the rover on Mars. It's called the Rover Decision Challenge, and the goal is to justify the best path with limited battery. So you're gonna imagine that you are an AI system controlling a space rover on Mars. As you can see on the slide, the scenario says one of two things. You can either be path A, you can use a shorter, less process time, but it's rocky and unpredictable, so anything could happen. Or path B, a longer but smoother and safer route. So you gotta pick, like, do you want the safe and long route, so it takes a lot of time and battery, or do you want the short route, save some battery, but you don't know, maybe the rover could get broken or anything could happen there. And so in breakout rooms, which Evan or Prateep, I'm not sure who's hosting the meeting,
I
but
think
one
we
of them
need
will be
breakout
leading.
rooms. We can just
But
do
one of
this
them is
in
Yeah,
going
we
here.
to.
yeah.
Okay, so we're not doing breakout rooms. I guess you're on your own then. But you're gonna decide which path you think the rover should take. Maybe like a quick 2 to 3 sentences to justify your answer using the battery usage, the risk, or the mission success probability. And yeah, you're just gonna probably like a quick 2 to 3 sentences about what your opinion or what you're thinking about this.
And officers, feel free to also participate in this. I'm gonna do that now.
Mm-hmm.
I'm gonna go on mute and lock in real quick.
Yeah, I also think I don't think there's any right answer for this. It's just that we just want to know what your opinions are on this. Personally, I think I would choose the longer path, even though that's worse for the battery usage. Just because I think like the rover getting broken is probably like worse than the rover getting discharged. I don't know.
I agree with you, Prateep. I would say the longer path is probably better. It will be a smoother and safer. The battery, regardless of that, it still would do its best to get to a destination, right? Um, and again, like the battery percentage in this activity, it wasn't like given, so, right? So we can just assume that it's low, but we can definitely use something like that time that's longer to potentially still make it to like our set point, even if it's a longer path.
I think they should also have solar panels, so battery won't be as much of a problem as we make it out to be. So
Yeah.
like anyone else?
No wrong answer, guys. It's all about making a good argument and maybe just like giving your opinion on it. That's honestly what it's about.
Well, I kind of thought of it as like the battery is like pretty low. So I feel like in terms of costs and stuff, I would have picked path A because I feel like I would trust the AI to make the right decisions in the unpredictable terrain while preserving my battery. But then again, I also don't know how the robot exactly would recharge if it did run out of battery on the longer route. So I would still pick path A.
Yeah, I agree with that. I would also pick Path A, probably because like assuming that the battery is low, I think considering that the rover can see its environment, I would trust the AI to make the right decision in the moment. But like I feel like a longer route, you're almost guaranteed to run out of battery. Whereas here, it's more of like a higher chance that you'll get through it with battery remaining. and I think that's more important right now on that mission.
Hmm. Anything else anyone want to share? All right, I'm gonna go to the next slide.
Yeah, let's move on.
Was this yours or mine?
I think it's yours.
Okay, so now we're gonna move on to talking more about the rockets, right? So this is gonna be like actually getting us to space or Mars or whatever. Why do rockets need AI? So rockets operate too fast and too complex for human calculations alone. So there's thousands of variables that change every single second, and every single second counts during launch. This is why they have to basically perfect this. Back then, they had human calculators, but now they actually have really good mathematical machines that are able to process things. This is what they're doing right now down in Houston, uh, in terms of NASA and SpaceX, right? Um, so that is why AI matters because AI reacts faster than human controllers and is able to basically control real time decision making during ascent, right? So like human brain, like we're able to think pretty fast, but what if, and it has happened, and it will happen, and it happens right now, right? What if the humans are able to create something that can think even faster than them, and like right now, everyone has access to a GPT right now, right? It can think super super fast. Now it may not be accurate, but it can produce something fast. So that's where we have to kind of see the balance of having something fast but also accurate. And it's something that that rockets need to have when they're ascending into space.
Flight path and fuel efficiency. So, AI algorithms also like optimize trajectories and streamline autonomous landing procedures. So, by using these, the predictive system health analysis is possible, which sort of like improves the maintenance schedules and reduces likelihood of failures. AI is also vital in managing reusable rocket systems because it reduces human error and increases cost effectiveness. All this contributed to a 12% increase in fuel efficiency. So, space organizations are definitely moving towards using AI for all of these because that is a pretty big cost difference.
Hmm. Also, talking about the costs, engineering, engine and monitoring and control. So it has benefited from AI integration in the past. There is some predictive diagnostics that reduce system malfunction by 10%. But by predicting and preempting potential failures, air systems have extended maintenance interval by 33%. So there has to be more maintenance taken into account. This is where, for instance, if you've seen online before, they're trying to make these massive data centers. That's basically what would count for like most like the maintenance part. They have to make sure that the integration is working efficiently for their systems, which will result in fewer mission disruptions and enable a more proactive approach to system health management. So that is helpful. Predictive maintenance has achieved a 30% reduction in engine failures, a 38% decrease in fuel tank failures, and a 25% drop in avionics system failures, and further reinforcing the reliability of AI-driven diagnostics. So overall, the monitoring of this has been working, um, but the percent could be higher. So there's still some room for improvement.
Now, we also have rocket engines designed by AI. So this is the Leap 71. It was headquartered in Dubai, in the UAE, and they engineered the Neuron, a large computational engineering model that enables the creation of machinery like this. So this aerospike was printed using a large, like a laser powder bed fusion thingy, and it was made using a copper alloy with copper chromium and I think zirconium. Yeah. So the aerospike was fired on December 18th, 2024, and I think it was a pretty good engine as far as I remember. Yeah, but next slide.
Mhm. So, keeping astronauts safe in space. So, astronauts rely on AI actually a lot in space. They make sure that there's good life support systems 24/7. It acts as like a constant guardian, monitoring O2 levels and carbon dioxide levels and pressure as well. Overall, crew safety for humans. It has to be able to predict problems before they become emergencies. So it needs to be able to detect um, any tears or rips inside of the spacecraft. It also needs to be aware of equipment that they're wearing or any habitat malfunctions or um, or yeah malfunctions. Yeah. Um, and this matters because in space, a small system failure or untreated medical issue um, can become quite fatal. There has been a few incidents in the past when it comes to these types of issues, but um, but AI can focus on prevention and early action, and it can protect a human life rather than just maintaining it for a long period of time. I actually want to show you guys something, so let's exit out of here first. Uh, let's just do window. Oops, wrong link. Um, I'm just going to show you guys what is on our Instagram page. We kind of touched on this already. This will not copy, guys. This will just like not copy. Um, just won't copy. Anyways, I might be able to just like go on here and see it. So this is Simon. So right back here. So Simon, which is right here. This is Simon right here. So what is Simon, right? So it was created in 2018 by IBM and Watson, used by NASA. It's a floating AI-powered robot assistant. Basically, is on International Space Station. So, like, think of those old cartoons that used to have like the robot cartoons, whatever. This is like basically what it is. It's called Simon. It's not called Simone, by the way. It's called Simon. So yeah. Anyways, so why is Simon important? Simon can support astronauts in extreme environments, voice-controlled task assistance, provides instructions for repairs, and documents missions and inventory. So yeah, um, that's Simon. Um, it's kind of cringe. It's 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 kind of cringe.
But show a picture of its face again.
Yeah, it's a little cringe, guys. Just yeah, make that make that your profile picture. And, yeah. Cringe. But it does help. It does help. You can go on BBC News and find it. So, anyways, um, all right, back to presentation. Um, yeah.
Okay, so now we're going to talk about the thermal control and radiation protection. Now, as you know, there's no atmosphere, obviously. So, like, in the space, so uh, astronauts, they have to worry about radiation from the sun, UV rays, sometimes gamma rays and stuff, and those are very harmful for our skin cells. They can give us radiation sickness and cancer and all that. So, we really have to be mindful about all of that when you're designing spacecrafts. And sometimes AI can also control and aid in like managing radiation within the ship. So they manage the heaters, radiators, and insulation stuff inside the spacecraft. It also tracks radiation coming from the sun. They're like visualized as like particle waves, uh, and they sort of like bombard the shields which are surrounding the spacecraft. Now, these are combined because temperature changes and radiation exposure happen all the time in space. So, yeah, it just has to keep protecting the spacecraft in real time.
Okay, so next is the Artemis and ISS life support. So going back to the slide we talked about here, kind of, ISS, which is still floating around our heads to this day, AI has to assist in recycling air and water to basically make it uh, livable for different humans or whatever. It continuously monitors gas levels in the environment. It has to detect problems before astronauts notice. So it has to rely very much on itself and its own thinking. And Artemis, which is the future or the next gen of Artemis, which it's actually trending on the news right now. But anyways, it's built for long-term lunar habitats and it's more autonomous. So they're probably gonna push it to go to Mars, maybe even past Mars, because they're trying to make it handle long-term lunar habitats. It's trying to basically have a limited Earth contact, so it's trying to go farther away from Earth, and it's supposed to manage again a life support and a minimal human input. The key point here is the that the AI life support is evolving from helping humans to fully sustaining them in space. And what does that mean? That means basically it's not going to rely on humans that much, right? Humans won't have to maintain it that much. Like the AI will be able to fix its own errors, right? It'll be able to learn from its mistakes. That's really what they want to aim for in terms of making um, this creation its own type of thinking and its own type of learning and relearning. Um, so yeah,
Thank you all
thank you for
for
joining.
thank you all for joining and
Yeah,
listening to us yap about space usage of AI and everything.
yeah.
Uh,
Now we forgot to put it on here. Two things. So the attendance form, I'll put that in the chat real quick for everyone to use.
yeah, I'll also send the feedback form in a while, because we wanna know y'all's feedback for this.
Yep. And also, as well, since you guys are here, and I hope you guys are listening to this, we're going to start our output in about 2 weeks. Next week, we're going to for AI in space, we're going to present more either on satellite imaging or we're going to do a coding workshop about this. But we're still going to reach out to you about that. And then the third week, which will be the week after next, we're going to start doing our output, which will for this week, it's probably going to be a research paper, but we're thinking about having you guys uh, sorry. We're talking about giving you guys three options, and those three options you guys can vote on, and we'll pick the best out of those three options for output. I'm assuming you guys are probably all going to pick research paper, which is probably the one that probably gets you the most amount of benefit in terms of you getting your work to be published on our website and be distributed to other people. But yeah, so we'll talk more about that, and Mokan will actually present a research thing on how to do research effectively for STEM. So definitely brush up your skills in research if you want to before next week. Um, and for that, you'll hear more information about the research project and stuff
Evan,
when you guys should have more time.
Akshan has a doubt.
Yeah, so I just wanted to like ask a little bit more about that. So this
Yeah.
research paper, let's say we do it, is it going to be like co-authored by everyone or individual?
No, it's individual.
Uh, yeah, it's individual,
You can choose to
but
collaborate with
yeah.
someone else if you know them.
Yeah,
Okay.
and we'll host a research session. Basically, we'll have me, Mocha, and maybe his Condor. We'll all get on the call. We'll basically present to you for about a few minutes. But then after the call, we'll kind of stick around. You guys can basically talk it out and share screens and just talk about what you need to do or whatever. So we're kind of here to guide you with that. We have experience doing research paper before, so you can always ask us questions about that. But
All
yeah,
right.
yeah.
But
If you
like
have
will
any
we
other
actually get this published is what I'm saying? Like not on the website, but like actually get it published somewhere.
Right now we haven't thought about getting it published officially like that. For now, we're just gonna keep it in our website. Additionally, you don't have to do a research paper if you don't want to do that. You can also do a poster or something like that that we can publish on our website because it will look pretty cool.
Right. But I'm interested in like a paper that I could actually show as published, you
Yes,
know,
we
like
understand.
actually on the
We will
website.
look into that. It's not this
Okay.
week anyway, so yeah.
All right, thank
We're
you.
gonna see if we can actually get it published or not.
We have about four partnerships right now, and two of them are actually associated with research and with professors. So I actually know a couple as well. So I can definitely reach out to them if you're concerned about that. We can definitely reach out to them and see if we can potentially work something out that we can publish this onto a faculty website or onto like an open source
Sure, that'd be great. We could
publisher.
probably talk about that afterwards or something.
Yeah.
Yeah, you can definitely reach out to us on band if you want to, because we're definitely, and like I get like what you mean, right? We're trying to get
Yeah.
ourselves out there, just like our website, right? We want to do that, right? This is like the point of this, right? So yeah, definitely reach out to us about that, because we do really want that to happen. Um,
Mhm. Okay.
yeah,
Thanks.
and honestly, we're still growing right now, so we're still trying to get more partners, get more members, and kind of get that swing into the direction of bigger opportunities, and but definitely like it will happen. It will happen. I promise you that it will happen.
I'm gonna end the recording now.